Yeah, Bappa, you can. And, and you can make me the host now. Um, okay. All right. So, so what I wanted to say is the following: that actually, maybe I should draw some pictures. So. So I'm just doing what we're doing now is just going to motivate later what's called the Levi-Civita connection on a Riemannian manifold. Okay, so we'll talk about Riemannian manifolds in a bit, but let me first talk about a manifold in Rn. So as always, let's look at S2. Okay. So suppose I have a vector field on S2. All right. So suppose, for example, I could take the vector field which is tangent to the latitudes. This vector field I could take, for example. So suppose M is a submanifold of Rn. And say X X, Y are vector fields on M. So we want to define the directional derivative or covariant derivative of y in the direction of x, right? So that will be nabla sub x of y. So this is supposed to be again a smooth vector field on M. Okay. Now the idea is what we will do is you can think of y. So this is a map from M to Tm. And Tm you can think of as a subset of the tangent space to Rn, because M is a submanifold of Rn. And this tangent space to Rn we know is a product, right? It's just Rn cross Rn. Okay. So here, this map, P maps to Y at P, we can think of it as of the form, a tangent vector we can write as of the form P comma some vector, which I'll again denote by Y at P. Okay. Where now I can think of Y as a map from M to Rn. Right? This is a smooth map. from M to Rn. Okay. So basically the point is that the domain of Y are points of M, but where does Y take values? At each point P of M, Yp is a tangent vector to M, but that I can identify as a vector of Rn, right? So therefore I can think of Y as a map from M to Rn. And now once I have a function which takes values, a map which takes values in Rn, this I can differentiate along any curve in M. Okay, so we can differentiate Y from M to Rn along any curve let's say gamma from minus epsilon epsilon to M. Okay. So here I can take any curve gamma. So Y will look something like this over here and maybe something like this here. Okay. This is my curve gamma. So I mean, so we can look at, let's say, so suppose gamma 0 is P and gamma prime 0 is V, a vector V. This a priori this belongs to TPM, but this is identified as a subspace of TPRN, which is identified with Rn. So maybe I should say something here that one little comment here that if M is a submanifold of Rn, then there is a natural identification of the tangent space to M with a subspace of Rn, of the tangent space to Rn. So why is this? Because, so suppose I have a submanifold. This is say M inside Rn. Okay. So I have the inclusion map I from M into Rn, the inclusion map. Okay. So the derivative of the inclusion map at a point P Yes, question. Local immersion. So what is your question, Bappa, exactly? I mean, you're saying that the tangent space can be identified if you have a local immersion, right? That is correct. If you have an immersion, then locally the tangent space can be identified with the subspace of the tangent space to Rn. That's correct. Yes. Okay. So we can look at the derivative of the inclusion map. That goes from TPM to TPRN. Where P is a point of M. And the point is that this map is injective. Therefore, it identifies TPM with a subspace of TPRN. And why is it injective? Because we have near P a local retraction pi. So let me call it pi tilde from a neighborhood U in Rn to U intersect N, where U is a neighborhood of P in Rn. Okay, we have a retraction such that pi tilde composed with the inclusion is equal to the identity of N. Why is this? Because what does it mean to be a submanifold? It means if I take a point P and I take a neighborhood U of P in Rn, then we have a chart phi from, we have a diffeomorphism from this neighborhood U of P to an open set V in Rn, which maps U intersect M to Rk cross a constant. Okay. This intersect V, this is equal to phi of U intersect M. Right, this is what it means to be a submanifold. Is this clear? Yes?
Yes.
Right. So therefore, over here, I have a natural projection, right? It's just the projection to the first k coordinates. So, so here I have this projection pi. And so what I can do is I can pull back this projection by the chart phi to get a projection here, pi tilde, right? That will give me my retraction pi tilde. So in other words, I conjugate by phi. So, so pi tilde is equal to phi inverse pi phi. Is this clear? Where pi from Rn to Rk is the projection to first k coordinates. Is this all right? Yes?
Yes.
So this will satisfy pi tilde composed with I is equal to identity of M, right? You see that? Okay. So therefore, what does that mean? That means that thus, if I by the chain rule, d pi tilde at P composed with di at P will be the identity of TPM. Okay, so di at P is injective. Is this all right? Okay. Yes. Is this okay? Yes. Are you there? Is this all right?
Yes, sir.
Yeah, you can reply when I ask if it's okay. Just you can unmute yourself and reply. There's no problem. So, that way I know that you're following. So it helps me if you reply. Okay. So for a submanifold, the tangent space is identified with a subspace of the tangent space to Rn, which is identified with Rn. All right. So now if we look at our vector field y on M, we've identified with a map taking values in Rn, right? Because the tangent spaces of M are identified with subspaces of the tangent spaces of Rn, which are identified with Rn. Okay, so therefore we can view it as a map taking values in Rn. And now we can just take its derivative. So nabla sub V of y at P. This will be ddt at t equal to 0 of y at gamma of t. So this makes sense because all of these vectors y at gamma t, they take values in the same tangent space, right? They take values in Rn, in the same vector space. They take values in Rn. So this makes sense as a vector in Rn. Okay, which you can identify with TPRN. But now, if we want to differentiate and get a vector field which is tangent to M, then what should we do? Then what we can do is we look at TPRN as, so we have TPM as a subspace. So we can look at the subspace, direct sum its orthogonal complement, right? Because TPRN, this is an inner product space with the usual inner product on Rn, right? So this is the orthogonal complement with respect to usual inner product on, so TPRN, which is identified with Rn. Is this clear? Right? So any vector V in TPRN, I can write as V as a component inside TPM. So that will be, I'll write V upper T for tangential and a normal component, Vn. Okay. So here V upper T belongs to TPM and V upper N belongs to TPM perp. Okay, so any vector in Rn we can split into tangential and normal components. All right, we can split into tangential and normal components. Right, so here here is TPM, which is a subspace of Rn, and we have a vector V, and there's a tangential component and there's a normal component. Okay, so this will be Vn, normal component, and this will be Vt. Is the picture clear?
Yes.
Okay. So now we can define nabla x, y as a vector field which is tangent to M, chi, so it's a vector field on M by, so nabla x, y at P. What we do is we take the derivative of y along the direction xp in Rn. So that gives us a vector in Rn, and then we take the orthogonal projection to the tangent space of M. All right. So this belongs to TPM. So we take the tangential component of the covariant derivative in Rn. All right. So this is how one can define a covariant derivative in a submanifold of Rn. Okay. So what we'll do is we'll get to this. We'll talk about properties of this covariant derivative. Okay. So the thing to note is, in order to do this, what we used is the metric structure of Rn. The fact that all the tangent spaces of Rn, they can carry a natural inner product, right? Because of the inner product of Rn and because of the identification of all the tangent spaces with subspace with Rn itself, right? So to define this covariant derivative, we're using the Euclidean, the inner product structure on Rn. All right, we're using the inner product structure on Rn. Okay, so now let me get back to the notes. This was some motivation. So let's finish talking about the covariant derivative in Rn first, before talking about the covariant derivative on a submanifold of Rn. So we'll see that it behaves nicely with respect to the inner product. So the first property is that if I take three vector fields, x, y, z, which are smooth vector fields on Rn, then if I look at the inner product between y and z at each point in Rn, that defines a smooth function on Rn, this inner product yz. And now x is a vector field, so it acts on smooth functions. So we can look at x applied to the function inner product yz, right? This just means the derivative of yz, the inner product yz, in the direction of the tangent vector x at p, at any point p, right? So this satisfies a Leibniz rule. This is equal to the inner product between nabla x, y, and z plus the inner product between y and nabla x, z. All right, so that means you first differentiate y with respect to, you take the covariant derivative of y with respect to x, and then take inner product with z, and then you add the inner product of y with the covariant derivative of z in the direction of x. Okay. So let's prove this. So, so this x applied to yz at p, this is the derivative of this inner product in the direction of any curve whose tangent vector at p is equal to x at p. So we can just take the straight line. Let's say we take the straight line in the direction of xp passing through p at time 0. So then we'll be looking at a limit t tending to 0, inner product between y at the point p plus t of xp. So this is the straight line passing through p in the direction xp, and inner product with z at the point p plus t xp minus the inner product yp zp divided by whole thing divided by t, limit t tending to 0. So now we use the definition of the covariant derivative. So it was a directional derivative along this straight line, right? So that means that y at the point p plus tv will be equal to yp plus t times nabla vy plus a term which is little o of t. So if we use that here, then we get that this y at p plus t xp, this will be yp plus t times nabla xy at p plus a term which is little o of t. Similarly, this z at p plus t xp will be zp plus t times nabla x z at p plus little o of t. Okay, and then we have minus inner product yp zp. So now we expand this inner product by bilinearity of the inner product. So the yp and zp term will cancel here, and then I'll get t times inner product nabla xy p with zp plus inner product yp with t times nabla x zp. So when I divide by t, the t will cancel, and then I'll get two terms which are, I'll get other terms which are little o of t. So little o of t with any inner product here divided by t, that will converge to 0. So finally what I'll get is this limit will be what I want. It's nabla xy at p, inner product zp plus yp nabla x z at p. Is this clear?
Yes.
Okay. All right, so we have this property of the covariant derivative in Rn. And now we have this other nice property of the covariant derivative, which relates it to the Lie bracket. So this is called symmetry of the covariant derivative. So it says that in Rn, if I take any two smooth vector fields xy, then the bracket of xy I can write as nabla xy minus nabla yx. Okay, so this is called symmetry of the covariant derivative. So let's do the proof. So you let phi t be the flow of x, So you'll think of this as a function of two variables, a real variable t and a variable in Rn p. Okay, so phi of t comma p is the function phi t of p. So then this map phi as a function of t comma p is C infinity. And so we can write phi of t comma p by applying the fundamental theorem of calculus in the first variable, which is just a real one variable in R. By applying it to t, we can write this as phi of 0 comma p plus the integral from 0 to t del phi del t of s comma p ds, right? And phi of 0 comma p is phi 0 of p, which is just the identity. So this is p plus integral, and then here I make a change of variables so that the integral from 0 to t becomes an integral from 0 to 1. I just make a linear scaling, a change of variables here. So then this will become integral 0 to 1 del phi del t of ts comma p into t ds. Okay. I just made a linear change of variables here. All right. My new s is the old s divided by t, so that the interval 0 to t becomes the interval 0 to 1. All right. Now, inside, I apply the fundamental theorem of calculus to this del phi del t once again. Okay. So then this becomes p plus t times the integral 0 to 1 del phi del t at 0 comma p plus the integral from 0 to ts, because I've got del phi del t of ts here, the integral from 0 to ts of del squared phi del t squared of some u comma p du, and outside I have a ds. Okay. Now, what is del phi del t at 0 comma p? That means ddt at t equal to 0 of phi t of p. That is exactly x of p, right? Because phi t is the integral curve of, is the flow of x. So phi t of p is the integral curve of x. So when I take del del t of this at t equal to 0, I'll just get x at p. So this first term will give me a constant here, x of p, which doesn't depend on s. And I'm integrating from 0 to 1. So it comes out of the integral. I get p plus txp. And then plus I have a t outside here times an integral from 0 to 1. And then this integral from 0 to ts, I do again a rescaling to make it an integral from 0 to 1. Then this becomes the integral of del squared phi del t squared tsu comma p into ts du ds. Is this all right?
Yes, yes.
Okay, so I have a t here, right? So this t will come out and hit this t and give me a t squared. All right, so to sum up, and inside I'll get some integral, which is a smooth function of t and p. Okay, so so finally I can write the flow phi t as p plus txp plus t squared times some r of tp. So in other words, phi t is equal to the identity plus t times x plus t squared times some r sub t, which is a smooth function where t comma p goes to r of tp. This is this integral from 0 to 1, 0 to 1, del squared phi del t squared, tsu comma p. And there's no t here. It should, this is a typo. It should be just s du ds. Okay. There's no t here. It should be just s here. Sorry, that's a typo. Okay. So this is now an equality of functions in Rn, right? And so if I look at d phi of t, the derivative of the flow, then d phi of t will be the sum of the derivatives of these maps. So it will, the derivative of the identity is identity. So d phi t will be identity plus t times dx plus t squared times drt. Okay. And now I look at what the Lie bracket of x and y will be using this formula for d phi t. Yeah, any question? Any question? Okay, so this Lie bracket is the same as the Lie derivative, Lxy at P. So this is the limit t tends to 0, d phi minus t at y of phi tp minus yp, the whole thing divided by t. Now I have this formula for d phi minus t, right? It's going to be identity minus t dx plus t squared dr minus t, right? In this formula, I just replace t by minus t. Okay, so this will be, when I apply the identity to this, I'll just get y at phi t of p. Then I'll get minus t dx of y of phi t of p, plus I'll get t squared dr minus t of y phi t of p. Okay, minus yp, the whole thing divided by t. So what do I get? I'll get y at phi t of p minus y at p, that divided by t, minus this t dx y phi tp will cancel with the t here. So I'll get minus dx y phi t of p. And then the last term, there's a t squared and I'm dividing by a t. So this will go to 0 as t tends to 0. So this last term will disappear with this dr minus t. This term will disappear because I'll get t squared divided by t. And so that t will kill it as t tends to 0. And so here, what do I have? The first limit is the directional derivative of y in the direction of along the integral curve of x. So this is nothing but the covariant derivative of y in the direction of x, right? So this will be nabla xy at p, this first term, minus what is this dx applied to y at phi t of p? As t tends to 0, this will be dx, this will converge to dx at y of p. But what is dx at y of p? That is the derivative of x in the direction of y at p. So in other words, it's the covariant derivative nabla yx, all right? So this will become nabla xy minus nabla yx at p. Is this clear? Yes?
Yes, sir. Yes.
Okay. So this proves the property of symmetry of the covariant derivative in Rn. Okay, so now we have again 1 minute left. So I'll just say what I'll do in the next 40 minutes after this meeting ends. So we've defined a covariant derivative for a submanifold of Rn. And what we'll show is that these properties of the Leibniz rule for the inner product and the symmetry of the covariant derivative in Rn, these are inherited by the covariant derivative of the submanifold in M. So the covariant derivative in M, defined as the tangential part of the covariant derivative in Rn, it inherits the properties of Leibniz rule for the inner product and symmetry of the covariant derivative. Okay, so we'll show that when we come back.